Look at modern infrastructure. We rely on massive loads being supported by steel beams that are by volume mostly empty air. To the naked eye, a loaded beam appears rigid and static, but inside the steel, the material is fighting a continuous, dynamic battle against invisible internal forces. When a beam curves under a pure bending moment, a rotational force applied to the ends, we rely on the Euler-Bernoulli kinematic assumption. It states that plane sections remain plane. Even as the beam curves, perfectly vertical slices through the material remain flat and straight. Simply watching the outside of the beam doesn't tell us when it will snap. To predict failure, we have to map the intensity of the internal stress at every single microscopic point within that slice. The survival of a skyscraper or a suspension bridge is strictly dictated by how these invisible geometric forces distribute themselves deep inside the core of the beam. Zooming in on the geometry of the bend, we can trace the curve of the beam back to a central focal point. The distance from this center to the beam is its radius of curvature, denoted by the Greek letter rho. As the beam conforms to the curve, the top fibers squeeze into compression, while the bottom fibers stretch into tension. Between them lies the neutral axis. On this exact plane, the material experiences zero stretching and squeezing. Its length does not change. We can measure how much the material stretches, a property called strain. Mathematically, this strain is the vertical distance from that neutral axis, y, divided by our radius of curvature, rho. Applying Hooke's law translates this geometric strain into physical force, normal stress, or sigma. Since we multiply the strain by the material's stiffness, or Young's modulus, the stress inherits that same linear relationship. Because the distance y increases in a straight line, the internal stress is perfectly linear. It is zero at the center and reaches its absolute maximum at the extreme top and bottom edges. A material's internal stress is strictly a penalty for its physical distance from the mathematical safety of the neutral axis. We isolate a microscopic area, dA, distance y from the center. To maintain horizontal equilibrium, every push in the compression zone is cancelled by an equal pull in tension. Across the entire face, these microscopic forces must equal exactly zero. For this mathematical balance to be possible, the neutral axis, the line of zero stress, must pass perfectly through the centroid, or geographic center, of the shape. These opposing forces act at different heights, creating a resisting rotational couple, the internal bending moment. We calculate this by multiplying the force by its distance y. Integrating across the face produces the integral of y squared dA, the second moment of area, I. Gathering these variables allows us to construct an intermediate equation. The total bending moment, m, equals Young's modulus E times the second moment of area, I, all divided by the radius of curvature, rho. The second moment of area, I, scores how well a beam's geometry defends against bending by placing material far from the center. In the real world, the radius of curvature, rho, is almost impossible to measure on a bridge or a building. We have to eliminate it. By substituting our stress definition into the moment equation, rho cancels out, leaving the Flexure formula. Stress equals bending moment, m, times distance y, divided by I. For maximum stress, we swap y for c, the extreme outermost fiber. Engineers possess the exact mathematical blueprint to predict the breaking point of any solid material under a bending load. We simplify this further by combining I and c into the section modulus, s. Every standard engineering shape has its own pre-calculated section modulus. Stress simply equals the bending moment divided by S. A larger section modulus directly results in lower internal stress. This reveals a massive inefficiency in solid shapes. The material near the neutral axis carries almost zero stress and does almost zero work. The I-beam exploits this linear stress distribution. Moving lazy material from the center to the extreme flanges maximizes the section modulus without adding extra weight. Entire cities and modern infrastructure are built upon this exact manipulation of geometry. We span massive distances not with more mass, but with intelligent shapes. Manipulating a material's shape is just as powerful as changing the material itself. But if the top and bottom flanges handle all the bending, what exactly is that thin middle web doing? That involves a different set of invisible forces: shear stress,